welcome back to the channel. In today's video, I've got a really exciting project for you. I've been receiving a number of requests to do more videos where I look at real data and demonstrate how these tools you've been working on will apply to that. And so I will do just that. The real data I will be examining will come from the Metabolomics workbench. And we're going to look at study ST002492, which was a study performed out of Northeastern and MIT, where they are trying to understand the composition of food and how the metabolic profile of these foods differ as a function of the sample type. And so the sample type ranges from apples and bananas all the way to black beans and olives. This data was collected via LC-MS, or liquid chromatography mass spectrometry. If you go to the MS tab, we can see more information on the chromatography. They're using a water acuity system. They actually have 4 different studies, 3 of which are reverse phase, the last of which is a helic approach. And then all of this was done using electrospray ionization on a high resolution Orbitrap, thermal Q exactly to be more precise, and then both in positive and negative ion mode. And the data, the actual quantitative data, are the peak areas of these various metabolites. And so this looks like a very traditional untargeted mass spectrometry experiment. And so I'm excited to dig into it. The actual data that we're going to look at can be found in the download name metabolite data file. And if we click the download data matrix, this is the positive ion data collected using reverse phase chromatography. You see that we have this table of data located on the web. And so in this video, we're going to use pandas to scrape this web page to get the data and then process it using a lot of the normal processing techniques we've worked at over the past almost 100 videos on this channel. So the key attribute of this page really is this URL so that we can use pandas to scrape it. If we zoom out far enough, you can see that this really is a data table, albeit a little messy and will require some cleaning. And so by the end of this video, we will be able to build a data-driven recommender where if we have an apple and we want to eat the most similar food to it based on the metabolic profile, our algorithm will sort these based on similarity to that apple. And you can see how we can abstract that to many other forms as well. I will put this Jupyter notebook on my GitHub page, and that link will be in the description. That way, if you have all these libraries installed, which you do if you have installed Jupyter using Anaconda, you can run this and it should work for you. It will begin as we begin every video, which is preparing our environment with pandas, Scikit-Learn, and then some of the plotting libraries we'll need, Matplotlib, Seaborn. And then we will build our recommender using sklearn metrics so that we can assess the distance between these various plant foods based on their metabolic profile. Next, we will access that data file using this path. So instead of locating the data on our computer, we will have pandas locate the data on the internet, scrape that down, and then store it locally in our memory as a data frame. To do that, let's do this as we always, and that it will be using pandas.read, in this case read CSV. And let's just begin with the path, and we will begin cleaning this up as we understand the data structure a little bit more. And then let's hop to side-by-side mode so we can see how we change the output of this table as a function of the various degrees. And so when we run this, the first thing you might notice is that we have these T's, these backslash T's present. Let me make the font a little bit larger. We have these backslash T's present. So this tells you that the default separator is not a comma, as is inferred by CSV. And so let's improve that as well. So let's change the sep type to backslash T to match this separator and look at that output. So pretty quickly we get to something that already resembles more of a table, which is a great step. And so let's now begin sorting out this header situation. Technically, based on the structure of this data table, there is no header identified by the read CSV. So let's specify a header. We'll do that by passing in the header argument, the index where the header is located as a list. In this case, the header we want will be 1. When we run that, you see that now we have a header row. Next, let's set the index column. So we do that by passing index call, and we'll set that equal to 0. And now we've moved this set of metabolites, these metabolite IDs, to the index. The next thing I'm going to do is actually assign this as a variable. So let's just set this equal to raw df. When we look at RawDF ahead, we have the first 5 rows of our data frame. It's not totally clean yet, but we also want to ensure that the bottom of our data frame looks suitable as well. So let's pass the rawdf.tail method. And you see that we have some missing values at the bottom plus some HTML tags. So let's make sure we get rid of that as well. To do that, let's use the outer parentheses and we'll just use the iloc method. The iloc is index-based location. And so we can just say all the rows except the last 2. And then we don't need to pass anything for the columns because we're not going to make any changes there. When we do that, you see that we now have no missing values at the bottom and our data frame looks a little bit better. So let's move to the next cell and do a little bit more cleaning where we will drop this factors row. We'll use that later because it looks like there is a relationship between the header column and this first row that appear to be sort of a key value pair that we can actually use to encode these variables here, but we'll do that in the next cell. But for now, let's drop this factors column and store that as a new data frame. So to do that, we'll just say rawdf.drop. And typically we're dropping columns, but we can drop rows. So we're just going to set the index argument equal to factors. And let's take that. And let's look at this again. Okay. So now this looks much better. Something else I noticed is that we have some missing values. And in this case, I'm going to assume missing values indicates that that signal is absent. And so I'm going to just chain in fill in a equals 0. Now this is not always the best case, but that is part of the assumption that I'm going to make. And if I were doing this on a real project, I would just note that assumption as part of my data processing. And now let's look at this, and we now notice that those missing values are 0. Next, I mentioned that there may be a relationship between those header columns and that first row in rawdf. So if we look at these 2 here, and so let's try to take advantage of that and this step here so that we can get rid of these cryptic codes and maybe just state Apple for each of them. So when we're going to be doing a lot of data processing, I like to wrap everything in parentheses so that we can see the change as a function of our various methods. Method 1, let's take this factors column and clean that up first. So we're going to do that by using this location method and pass in the row we want to isolate. When we do that, you see that we now have this series where we have our column and the first row. It comes back as a data series, you can tell, based on this name argument. And let's begin cleaning. So we've done this process before. The first thing we want to do is let's get rid of species. And let's get that colon 2. When we pass replace, the first string is the pattern we want to get rid of or we want to look for. The second string is the replacement key, the replacement pattern. In this case, you just want to replace with an empty string. When we do that, you see that species is gone. Now let's replace, actually, let's not replace, let's split on the vertical bar. And the output of that varies as a function of these arguments. So when we just pass this in, we get this list here, but we really want to extend this so we can actually separate it much easier. So let's just pass expand equals true. When we get that, we have a data frame that's returned where we have column 0 and 1. We really only want column 0. So the nice thing about that is we can just pass in the 0 argument and return just that. Now, this is maybe a deceptive view because what happens here is that it appears that there could be white space after this apple. And that's because I think around this bar there was a space on either side. But in case, I want to show you how we can get rid of that. Well, let me show you how we can determine if it's present. So if we look at row 0, you see that we have this space here, which could make it a challenge when we want to look for the apple, and the apple actually is apple plus a single white space. To get rid of that, let's just pass in str.strip. And you see that that removes the trailing white space. And so now we have a really good key value pair that we can take advantage of. And let's set this equal to a data frame. We've done that before, and we now have this. And let's pass in a name called sample ID. And so we're going to leverage this to build out our original data frame that we made above as df. And so we're just going to call this one sample information, sample info. And let's just remind ourselves what this looks like as we move forward. And I know I'm going fast, but I'll have this whole notebook in the GitHub below. And if there's something you have a question about, leave a comment and I will address it. So next, let's remind ourselves what the original data frame columns look like. It's these cryptic keys. And so we really want to replace those with our new columns, which will be from sample info. So to do that, we will set df.columns equal to df.columns.map sample info. And let's look at our data frame now. And so now you see that we have what appear to be triplicates of each of our samples. We get out of side-by-side mode, so we can have a larger view. We have 3 apple injections, 3 banana, 3 basil, etc. And this is a much cleaner data frame from which to try to build some insight from as we continue our data processing. The next thing I would recommend is double checking the D types. Let's make sure we have a good sense of our data frame. And quite surprisingly, all of this numerical data is actually not numerical at all. It is a object data type. And the reason this could be a hindrance is that if we try to compute the mean, we get this issue saying that there are no numeric values. Mean only works for numeric values, so there's nothing output. And so let's just convert everything to an integer. Yeah, let's just do that. And so let's say df equals df.asType. And we just pass in int. And we'll do this again. Look at the D types. And you see that now everything is integer 64, and that makes it suitable for us to do our data processing. Even though visually it looks the same, the underlying data type has changed. So one thing to note is that in this case, I don't necessarily care about the triplicate injections. There are cases where we might do that, and we could, assess the relative standard deviation of each of these measurements, but that's not really the scope of this video. In this video, I want to be able to take the apple out of my data set and then see which other botanical or which other plant food is most similar. And so what I want to do is aggregate based on my column headers and just compute an average value for each of these metabolite signals. So to do that, we're going to use group by. Chances are you've seen people group by various rows, but you can also group by columns. And so we can take advantage of this common column header. So let's do that. So we're going to take df.groupBy, axis equals 1, and level equals 0. So we're saying group by the columns and take the 0 level column header. In this case, there's only 0. If we had a multi-header, let's say we had tree fruits, and then under that we had apple and banana, and then we had herbs, and under that we had basil and other herbs here, that would be a level 1, a level 0, and a level 1. Here we only have level 0, but we can change that. And if we group by that, we will get a generator. And so when you see this, you need to think we need some way to iterate or a computation. In this case, let's just take the median value. And so it'll aggregate based on the column header and then return the median value of each of these measurements here. So let's call this group df. And if you're enjoying this video, like, subscribe if you're not subscribed. Like I said, I know this is a longer video, so I will have this notebook in the GitHub in the description. Instead of building a recommender based on all these variables individually, this data is a really wide data set. So if we look at df.shape, we have basically one sample per each variable, kind of a 1-to-1 ratio. And so the statistics are kind of against us in this case, this curse of dimensionality. And so let's reduce the dimensionality and give ourselves a better chance at building a suitable recommender. To do that, we are going to use PCA, and that is why we often use PCA. That's really to shrink down our variables. But our data is not structured right. So the first step is to transpose the data. When I get into the model building phase, I convert my data frame nomenclature to X and Y so I can track what I am working with. So let's say X equals df.transpose or df.t, or not df, group. So you see that all we've done is transpose the data frame. So each row is a sample and each of my columns is a variable. Now let's begin computing our PCA components. So let's say n components equals 4. And oftentimes I like to generate a list for my PCA columns. And I will do this using a list generator. Let's just say PCA calls PCVal for val in range in comp. That's number of components, and actually say val plus 1. It's because when I range, it'll range from 0 to 3, but I really want from 1 to 4. Just that makes more sense for this particular reason. And so if we look at PCA calls, you'll see that we have PC1, PC2 up to PC4, and if we change it, this will change accordingly. I also imported a pipeline method, so we can actually just chain together our standard scalar and our PCA. To do that, let's just make a variable called PCA pipe, and let's set that equal to make pipeline. And in here, we will just pass in a list of our pipeline components. So let's say standard scalar. We won't tweak that at all, and we'll just make a new row so you can see what we've got. And we'll say PCA, and here our arguments are number of components, and so we'll just set that equal to n comp. And if I run this cell now and just pass in PCA pipe at the bottom, this will show us what our pipeline looks like. So if we had multiple steps and column transformers and other components there, we could actually see this and see the parameters. So it's kind of a cool way to keep track of your model, especially if you're piping together multiple steps, if you did not know. Okay. The other thing I want to do is set the transform output so that we automatically generate a data frame. If you have a newer version of Scikit-Learn, this is something you can do, and it's really convenient. So we can just set the set output method, and in here we pass in the argument transform, and we can set that equal to pandas. That way, instead of the default NumPy array that's output from Scikit-Learn, the default output would be a data frame, which we can take advantage of and make the rest of our processing much easier. So let's run our model. So let's say PCA pipe, and this is the same way you run every Scikit-Learn model, fit transform. When you're fitting the model, it will pass in X. And again, I like to use the common nomenclature, so I'm not trying to recall what my variable names are. If you look at scores, the output of scores is a data frame. Normally we are creating the data frame from the array, and thus I can set the column attribute to PCA calls. This will overwrite it. And if you look at our data frame again, our columns are, I was passing the right method name, columns. And we update this, and you see that now we have our columns, our PC1 through 4 from here. So a very convenient way to get your data in the structure that you prefer. The other thing I want to do is set my index, so scores.index equal to x.index, and that is from our original data frame. And you see that now we can track our samples as a function of our PC components. And so what I want to be able to do is, again, pull the Apple sample out and see what is the best replacement based on the metabolic profile. And we're going to use the PCA data to give us some sense of that instead of looking at all 69 variables. I'm going to now plot this data and then set up sort of our little lo-fi recommender system. And it's going to be kind of code intensive, but again, review this and see these steps and appreciate them more. If you have comments or maybe even a better approach, feel free to let me know, and I'd be happy to take a look. So to create our lo-fi recommender, we need a way to assess the similarity between our test material, some material we pull out of the data frame, and the rest of those remaining materials. So to do that, we're going to use that pairwise import here, this pairwise distances as dist, and create a distance matrix. And so let's say dist, we're going to pass in scores, and then we're going to pass in a distance metric, and we're going to just set this equal to Euclidean. And let's look at this. So this is our similarity matrix. The output is a NumPy array, and so we want to now convert this back to a data frame. It'll just make the plotting easier. Then we can set up our recommender. To do that, I'm just going to wrap everything in this data frame structure. So pd.dataframe. And now you see that the similarity between apple and apple is 0. The similarity between apple and banana is 0.72. Apple and basil is 17. And now we can leverage this relationship to figure out the similarity. And this is again based on the scores data. So these 4 components there. So let's call this simdf. Let's look at simdf.head so we can keep track of what this looks like. And let's begin our actual recommender. To do this, we're going to create a couple plots that we can sort of visualize this as we are making recommendations, and then see the similarity in the context of the entire suite of plant foods. The first plot I want to make is a scatter plot of the PCA data, because that is the sort of source data for the similarity matrix. So to do that, let's use subplots. So fig, here we're going to set in calls equal to 2. These would be side by side. And let's set the width, because the way I'm thinking about this, the scores plot will be larger than the similarity plot. Let's set the width ratio to 0.65 and 0.35. So this would just be how much of that set space it takes up. We'll set the fig size equal to, what seems reasonable, 12 by 6. Let's try that. And let's keep going. So all we have now is an empty figure. And in that figure, we have 2 axes, axis 1 and axis 2. And you can see that width ratio coming into play here, with this being the larger side and the smaller side. Next, let's make our scores plot. And because we might want to look at various components, we'll just set variable nxvar equal to pc1. And we might modify that later, yvar equal to pc2. Test food, and this would be the food we want to replace, equal to, let's start with apple. That's a good one. And now we've done nothing yet for the plot, and so let's set our plot equal to sns.scatterplot, and x will equal scores xvar, and say y equals score will equal score yvar. And let's take a look at what we've got now. So when you don't specify any other parameters, by default the plot goes to the last axis that was created. In this case, it was axis 2. So let's set our x argument here equal to x1. And that will put it on the left chart. But we need more information, coloring and in some way to sense what the actual test material is. And so I want to create a color map. Let's just call this CMap. And we'll have another list comprehension where we would develop a color map based on test food. So if the variable equals test food, it'll have a different color than the rest of the sample in our score plot. So let's CMap, we'll do a list comprehension, and let's just call it test. So test food, if val in test food, and so if else other. So if it's not, we'll just call it other. For val in scores.index. So we're going to look through the scores index, so this list here, and see if test food matches one of these values. If it does, it will call that test. If it doesn't, it's going to call it other, and we're going to use that to actually map the color. That's all this is for right now. And so we will set the hue argument equal to color map, and we'll run that. We run that, you see that this looks okay. We can tell that this is our apple sample. Let's change it to basil. And you can see that it's not so okay. So the color map changed because it when apple is the first argument in our data frame, it assigns one color map versus when basil happens. So let's lock this color map in using an argument called hue order, and we can pass in a list that will take advantage of this. So the hue order will always be test, then other. So no matter when test appears in the list, it will always get the first color in the color map, then other will always get the second color. And if we run this, you see that our hot color is blue. If we change it to basil, our color map stays the same and our test sample is blue again. So this is what we want. The next thing we will do is also take advantage of size. So let's just set size equal to, we can set it equal to CMAP, so we'll just specify different sizes, and let's set our size. You can see here it's setting it other larger. So sizes is where we can pass our list of sizes, 200, and let's set size order as the same list. So now our test sample will be larger, and our other materials. And so quite a bit of code just to get the figure to look the right way, but this will help tell a compelling story. We can see where this is in the context of all our other materials. The last thing I want to do is now sort this. So to sort this now, we will make another scatter plot called st.scatterplot. We will set x equal to 0, so we will just have a line plot, and we will set y equal to our similar data frame where we look at test food. Test food will be apple or basil or some other plant food. And we'll set x equal to ax2. And now you see we have a sort, but this is missing a lot of context. So let's improve this enough to give our stakeholders some idea of what we're plotting. To do this, we want to set our title equal to an f string where we have, we're looking at the similarity. So now we see we're looking at the similarity apple, but this is still missing some context for us. So let's also add some y labels to this plot on the right. To do that, we're going to do set y label. So let's just set that equal to Euclidean distance. And we can see that this is looking pretty good. But we need to do a little bit more as well. And so one thing we do is add sns.setTheme, and that improves the overall layout just enough. And so the next thing I want to do is annotate our particular plot on the left so that we can see how to plot this. And it's going to take quite a bit of code. So again, review this notebook in the GitHub page. To do it, we're going to use a for loop and loop through. We're going to use an ax2.annotate to actually apply the annotation. And then we'll set a little bit of wiggle so that our points don't overlap too much. And so we'll just set an x offset equal to negative 0.014-ish. Doesn't necessarily matter, and just kind of play with that parameter as you continue. Let's see what this looks like. Now that we look at this, let me get out of side-by-side mode. We have apple down here at the bottom. And so apple is down here where Euclidean distance equal to 0. And the most similar samples to apple are pear, peach, banana. The way this works is that now if we switch to something like carrot, you can see that carrot is here, and the most similar sample to carrot would be lettuce, pepper, and corn. Maybe surprising, maybe not, but I also want to annotate this figure as well. I think it'd be nice to see where this is in this 2D plot. And so we can apply a similar for loop approach where we are going to loop through not our SimDF, but our scores data frame. When we annotate that same for loop, you see we have ax equal 1. Most of this stays the same. We've used iteros before to iterate through our scores data. We're going to specify which PCs we're looking at or which columns we're looking at based on our xvar and yvar, and unpack them accordingly. When we do this, we can now see how this data is computed. So in this PC 1 versus 2 in that scores plot, we see that the carrot is closest to pepper and lettuce. And remember that the distance is also computing based on PC 3 and 4, which we're not showing here. The last thing I would want to do is also provide some more context on this particular plot as well. So to do that, I'll use set title and an f string, and we'll just tell the end user what the test food is, the x variable and the y variable, and close this up. You can see now we have our PCA scores plot color by carrot, similar to carrot, PC1 versus PC2. Here's our test material, and here's our similarity linear scatter plot. And so now you can see how we're building what looks like a lo-fi recommender system using data we scraped from the internet. And now you are able to really build your own insights, maybe not just looking at one data set, but multiple data sets. So if you enjoyed the deep dive, let me know. If there's other data sets you want to explore, let me know. I know this is a longer video, so thank you for sticking with me, and I'll see you in the next one. Peace.